Right, welcome back Physics 30. Last time we talked about decay and how we can calculate some of these energy to a momentum calculation during a decay, and then a specific decay reaction that we look for is alpha decay. Now we're going to look at our next two different type. One is known as beta decay. Beta decay has two different parts, beta negative and beta positive. So think about this as 2-1 and 2-2. And our last type, gamma decay. Last lesson was quite longer than others, so today's lesson should be a little bit shorter. All right, so let's talk about beta decay. Now, beta decay involve excited electron. Now, electron, as you may know, is something that doesn't have an atomic mass, because atomic mass should be proton's mass, not the electron's mass. So, because mass of electron is smaller than proton, beta negative particle is notated as beta with -1 as a charge at the bottom and mass number as 0. That is what beta negative is. Beta positive, this is something that you may not seen before. It's known as positron. It is something like, how can I say? It's exact same size of electron in terms of mass, but instead of charge as negative, it has positive. It's known as antiparticle of electron, which we're going to discuss more during quark. And beta positive, same thing. Electron's mass is smaller than proton's mass. Same thing for positron. So that's why the notation that we use is beta, +1 at the bottom and 0 at the top. Now, that's basically what it is. Beta decay, negative, let's look at that first. First thing first, decay is happening because small particles are emitted out of original atom. Now, in nuclear force, there are two different types of force. Strong nuclear force is nuclear fusion. That's like hydrogen make helium, something like that. It's plus situation. Nuclear fission is opposite. You are having, let's say, helium and then turning into hydrogen and hydrogen. It's actually division. It's basically breaking apart. When things are breaking apart, we name that as weak nuclear force. And whenever weak nuclear force, it happened because nucleus has quite many different numbers and kinds of neutron. Sorry, kinds is a bad word. But long story short, nucleus has many neutrons. And these neutrons can be emitted outside, or it can be break into some other pieces. A neutron changes into proton or high energy electron. And that's what makes beta decay happen. So, first thing first, due to weak nuclear forces, neutron is emitted. But neutron, when it's emitted, it changes form into a proton and emits high energy electron, which is beta negative, and antineutrino. This antineutrino is quite significant. It will be discussed later. This is known as antimatter, where, long story short, scientists detect the evidence that there is a matter occur and matter turning into an energy like mc squared, but we found the opposite of that energy, which is, some people say dark matter, dark energy. Think about that concept. We know it's existing. We don't know how that's applied, and that's quantum theory that play a huge role in atomic physics. So have that in your mind, and we're gonna not talk about the origin of these matter. We're gonna, if you want to memorize, feel free, memorize or calculate in terms of beta decay and how you balance. So Let's look at the quick example. We have a parent molecule and daughter nucleus. So parent nucleus, daughter nucleus. So this is sodium 24. And when it comes to daughter, that's magnesium 24. Note the fact that 24, 24, there's no mass change because, first thing first, beta negative doesn't have any mass number, and so as antineutrino, it's 0 and 0. Then what does it change? It changed the bottom number, charge number. How can the charge different? Well, think about this. Beta is negative, so negative plus 12 will make 11. So that's why conservation of charge is the reason why we can only balance the bottom number, not the top number. Top number doesn't change. And antineutrino, the notation is V with line and O and O. That's how you notate antineutrino. On the other hand, there is a concept known as neutrino, and that part will come out in beta positive. Beta positive is like what you see in the previous one. Due to nuclear weak force, proton turns into neutron, and the neutron turning into positive entity having an electron, which is known as positron, and neutrino. And those two doesn't have mass, so 0 and 0, which means the top number, 15 and 15, doesn't change. Oxygen 15 turning into nitrogen 15. Why oxygen change into nitrogen? Is because of my conservation of charge. As you may notice, the bottom number is 8 for oxygen. That's its proton number. Now beta positive plus 1, so we need to match these two numbers, 8 and 1, so it must be 7 for my daughter nucleus, which is nitrogen. And neutrino doesn't have any of a positive or negative entity for charge or mass. It's just matter that people detect it. And basically energy is released during these two processes, and energy can be turning into EMR energy. And that's something that you may want to know. When it comes to gamma decay, this is an easy part, if you will, or it's something that is used for calculation a lot of time. One thing that you need to understand is during alpha and beta decay, the nuclear can be left in an excited state. And if you think about Bohr atomic model situation, if you are excited, then relaxed, what's gonna happen is electron that is occupied from an upper level will travel to lower level, and during this process EMRs are emitted. And if you think about decay situation, gamma decay is talking about this last half. Excited stage is unstable, so in order to be stable, electron will return to lower level, generally ground state. And by doing that, EMR is emitted, and that's high energy EMR. It's gamma radiation. So the property doesn't change. It just emits very high energy EMR as it relaxes, basically. So when it comes to notation, you may notice X and X. I put the same thing because element doesn't change, but I have little star for excited to relax, and during that we emit basically a EMR, which is gamma radiation during this process. And of course, when it comes to this situation, we can use E is equal to HF or HC over lambda. It is your choice which one you use. And when a radioisotope go through alpha decay as an example, then there's two possibilities. Number one, only an alpha particle is emitted with very high energy, or alpha particle emitted with lower energy, but daughter nucleus is in such an excited state, it's going to relax and emit some kind of EMR energy, which is gamma, photon, something like that. So energy is somehow distributed either to alpha or EMR. Let's do some example. Use balanced nuclear equations to answer the following. Indium-115 undergoes beta negative decay. What is the daughter nucleus? So make sure you are preparing your periodic table. Indium is located at 49 of your periodic table. That's number of proton. And we have 115. This guy undergo beta negative, which means I have beta negative at the bottom and 0 on the top. And anti-neutrino, that's an antimatter that emit. Followed by, we need to now talk about the daughter nucleus, which is like a fill in the blank. On the top, you should understand that it is still 115, because top number doesn't change. But the bottom number, I know it's negative, but in the end, we should add it up to make 49. So there's only one way. Bottom number should be 50, which is 10. So my daughter nucleus is turned out to be 10-115 is my daughter nucleus. That's how you do. That's how you balance nuclear equation. Let's do more. Nobelium-255 decays to which isotope of fermium? Well, let's talk about each of them. Fermium is my daughter nucleus, so we know what things are what. Nobelium is NO. It's located at 102 of your atomic number, so that's proton number. And mass number is 255. The fact that fermium Fm is that means we know the bottom number for sure, which is 100. We do not know the top number, but we need to also identify what things are added up to there. One thing that you know is, can you see it's 102 versus 100? There is only two difference, and that means my particle that is emitted during this decay must have 2 at the bottom, which is only one situation, alpha particle. Or you can put 2 for helium, it really doesn't matter. And when it comes to this situation, 4 plus something that make 255, so it should be 251 that goes in the box over there. So we have alpha particle, sorry, it turned out to be alpha decay. And when it comes to the previous one, that's beta negative decay. Oops, I forgot. Possible gamma particle. Gamma radiation. There you go. Let's look at C. When a parent isotope undergo beta positive, so we know what things are emitted. The daughter is nitrogen 11. So it's like going backward situation. Nitrogen 11, that means 11 is on the top. And at the bottom, you should have its nitrogen number 7 in here. Plus, since it's beta positive, oops, I'm going to rewrite. 0 on the top, positive 1 at the bottom. That's beta positive. Plus neutrino. Plus gamma radiation. That's what we have. Now, we just need to add the bottom number and top number. Top number is 11. Bottom number is 8. So that's just one more right of nitrogen, which is oxygen. So my parent nucleus turned out to be oxygen 11. That's what you need to do, folks. Lesson for today, I want you to work on every questions from homework both A and B on page 9. Do everything on that. Followed by page 10 and 11. That is today's lesson.